seems to do that once every couple days. All right. So the first one was mass, and we've established that answer. The next one was weight.
His weight definitely changes, right?
Why? Why do you say that?
I say that just because I'm not gonna have the right words.
That's okay.
Okay, so they're going downwards. So when it's not at a constant speed and you're going downwards, speeding up, his weight is gonna be greater, right?
Like how you were talking about that one time, like jumping on a scale, or like when
Yeah.
you're in an elevator, your tummy kind of does that little tickle thingy, you know? Where you get like butterflies.
Oh,
Is that just me? But I feel like that's because the weight is changing. Or maybe I'm just overthinking it. What are the
you're
butterflies?
running into a conflict over what exactly is weight. So, Ariana?
Yeah, the weight remains the same through the whole thing, because the weight is from the earth onto, like, the weight is the earth's pull on the man and not the elevator or anything else. So the difference in force when you're jumping on a scale or any of that is it measures the normal force, not the weight.
So, and part of the problem here, first off, what's the formula for weight?
Weight equals G.
I heard, I want to hear Bill Haas say it.
Mass times the acceleration due to gravity.
Okay. And somebody else just did the initials?
W equals mg.
So we've established the mass isn't changing.
Yeah.
Is the acceleration due to gravity changing?
No.
Not significantly. And I can't remember if I actually put the wording in there. You could make an argument that you are closer to the earth, and therefore your acceleration due to gravity is greater than you are on the 10th floor. But you need multi-million-dollar equipment to notice that, to actually measure that difference. So we are assuming the acceleration due to gravity is constant.
So B is,
Same.
they're equal to?
Indeed.
What is the tickle in your tummy that happens then?
That is,
Inertia?
yeah, I mean, there's a lot of different things you could
Wow.
lump it into.
We already
You're-
did this.
What actually happens is your stomach changes position in your body, so what you're feeling is your stomach moving around.
All right then.
There is I mean, if you throw it into the inertia point of view, is that, I mean, you start out at rest and your stomach is basically at rest. And then when the elevator starts to drop, because of the inertia, your body wants to stay where it was, but it's not happening. So in essence, depends on which part of the body starts moving first, but if your stomach stays where it is and the rest of your body comes down on it, then you're basically pushing your stomach down.
That makes sense. I didn't,
I mean,
I
say-
never thought about it like that.
In a much more vicious, sorry, I had a friend killed in a car accident, but the physics of it is that what often kills people in a car accident is that the heart keeps moving when the body stops very suddenly. And so it's that can cause, I mean, there are other things also in an accident which can kill you, but that's one of the things that can kill you is the inertia of your heart when you keep it going at a constant velocity.
Makes sense.
And it's probably been 20 years and it still feels fresh to me. All right, so, I apologize.
No, no need to.
All right, so now part of the conflict here about what weight actually is Hewitt contradicts himself. And I make a comment in one of the commentaries that he does this, as well as, from my point of view, that's the formula for weight. And weight is that gravitational pull. And I thought, okay, the definition of, what is the definition of weight? If I went to, an official physics dictionary, what would it say? And they're in agreement with me. Now, what Hewitt does not distinguish between is what some books will call weight and apparent weight. The apparent weight is what it feels like. And then the actual weight is mg.
What do you mean what it feels like?
In other words, what does the scale read?
Okay,
So this right here, this is sometimes referred to, not by Hewitt, as the apparent weight. And I don't know if I spelled apparent right or not, but I will assume you corrected in your notes.
We get the gist.
I hope so.
I mean, I've
Well,
seen
by
that,
spell check.
I've seen apparent weight somewhere, it's just, I never really understood it.
Okay.
But it's what it feels like?
Yes.
Okay.
So if it feels like you're, because when the elevator first starts, it feels like you're a little bit lighter.
Yeah,
And so your apparent weight is less than what your actual weight is.
okay.
And then as you're stopping, it feels, you know, the thing that makes you do this, it feels like your weight's a little bit more than normal. So your apparent weight is more than your actual weight. And so scale is reading apparent weight, and as mentioned in one of the videos, that's what this normal force is. Because the scale can only read the force you act upon it. This is the only force the person is exerting on the scale. His weight is not exerted on the scale, the normal force is.
His weight is to the ground, right?
Yes.
Okay.
So, but you're ranking what this, what the normal force between him and the scale is.
Yes,
Yes.
magnitude of normal force he exerts on the scale, and then D is on the elevator floor.
Alright, so. F equals MA. Which law is this?
Newton's third law.
Or-
Or second law, second law.
Yeah, thank you. Newton's second law. I will ask students I've had for a while, and I say, hey, Newton's second law, and then I do my hand gesture of indicating, just shout it out, and I get blank stares back, and then they just randomly guess one of the laws. Yeah, it's really helpful. There are a lot of laws, like Kepler's laws, I can't keep straight, which one's which. I go through moments where I get them straight, and then it's gone 10 minutes later. There are a lot of other laws that really the order in which you do them gets kind of nebulous. But with Newton's laws, those are pretty well set. Newton's second law is Newton's second law in every single textbook that ever mentions them. I guess with the exception of, my son had a textbook which only mentioned 2 of his laws. I can't remember which one they left off. So the net force and the acceleration are in the same direction. So, while he's going down, what is the direction of his velocity?
Negative,
Why negative?
because I'm assuming up is positive.
Okay. And so why is up positive?
Because you start at 10 and you go to 1.
That's just what we chose.
Or more specifically, that's what Brianna said.
Yeah, that's what you said.
Because Brianna said so.
DBSS.
Alright, so
Let's start
velocity is negative because you're going downwards. Again, the sign of velocity is the direction you're moving. So my velocity is down. My velocity is down. Velocity is down. Alright. If I'm speeding up, is acceleration in the same direction as velocity or opposite?
Same.
Wait, why would velocity be going down in the middle if you're at a constant velocity?
You're still moving down.
Okay, I got you.
Yeah, I noticed that there are a number of students still getting velocity and acceleration backwards, or not necessarily backwards, but using them interchangeably. Velocity and acceleration, not the same thing. Acceleration deals with the change in velocity, not the velocity itself. So since I'm speeding up, my acceleration is also downwards. And then when I'm slowing down,
Or opposite.
and then at constant velocity, what's my acceleration?
0.
Now, I have 2 forces acting on the person. I have normal force acting up, and I have weight acting down. If acceleration is down, the downward force has to be dominant. If I'm accelerating up, the upward force is dominant. So in that first region right there, weight is dominant. But my weight is constant, which means that my normal force has to be getting smaller as I'm at the beginning.
Can you say that again about which force would be dominant?
So the dominant force will be the one in the direction of acceleration. A lot of times you figure out what the dominant force is and then go, oh, acceleration is going that way. Here's an example where we figure out the direction of acceleration first and then go, oh, okay, that tells us about the forces. So at the beginning, we're speeding up, so acceleration and velocity in the same direction, so your acceleration's down, or negative. These are the two forces acting on the person, and since the acceleration is downwards, weight has to be bigger than the normal force. Or normal force is less than the weight. Since our weight is constant, probably better to word it in terms of normal force. In this midsection right here, when acceleration is 0, they're balanced out. So normal force is equal to the weight. And then in the last section, acceleration is upwards. And therefore the upward force has to be bigger than the weight. And so the ranking of the force he exerts on the scale
Yeah.
is this, it's equal in magnitude to that one. So this is the largest down here, second, third. Or think about last time you were on an elevator, which during the pandemic could have been a few years ago. When it first starts, get on the top floor, you feel the stomach sort of move up relative to you. In reality, your stomach is trying to stay where it is and your body pushes down on it. That you feel a little bit lighter at first, and then it feels normal, and then when you stop, there's that, your body wants to keep going down, but something's stopping you. Well, that's what's stopping you, I hope.
The normal force is stopping you?
Yes.
So
If it
would-
didn't, you would just keep going through the floor of the elevator.
So.
But it wouldn't change between the scale and the elevator floor, it'd be the same, right?
Does there have to be contact between two things for there to be a normal force?
Yes, there does.
So there is none?
The last one wasn't scale and elevator, it was person in an elevator, right?
Yeah,
Yeah.
magnitude of normal force he exerts on the elevator floor.
Yeah, he
There is
doesn't,
none.
there's none.
Okay,
Wait, what?
because normal force, there has to be contact
No,
between.
no, last
two
one doesn't
things.
say that. Mine says magnitude of normal force he exerts in the elevator floor. Yeah. Oh. Bro, what?
It was a good day there
Alright.
for a minute.
And Hope, were you about to ask something, or Abby? I heard some voice over here.
No, it was answered.
Okay. You said it was answered?
Yeah.
Okay.
Thank you.
You have to have.
Since I'm hearing most of the talking over there, and I've been standing over there, why don't I stand over here for a moment? Any questions on this side?
That just fried my brain.
I'm not sure about the first question. I have a copy.
All right. Before we do the first question, any questions on the elevator problem? Other questions?
I have one, but it just slipped my brain.
You said you forgot it, or,
Oh, I'm talking to myself, sorry, I forgot it.
okay. I'm not trying to rush you, but I'm gonna answer Bill Haas and then.
That's fine, that's perfect.
Yes, ma'am.
So the question is, okay, a man standing on Earth and he has a force on the ground and what's his acceleration on Earth? I understand that, but I don't understand what will change if he was on the moon.
I conducted an experiment on the Earth, that one.
Yeah.
I push on my 70-kilogram partner, I'm standing on a frictionless horizontal floor, of course, with 100 newtons of force parallel to the ground, what's its acceleration on Earth? So in that case, frictionless, and so he was 70 kilograms and 100 newtons. Recognize there's three forces acting on the person. What are the other two forces? And, yes. I heard it over here.
What did she say?
Normal force and weight.
Did you hear that?
Mm-hmm.
Okay. So if we do the force diagram on the person, I have weight acting down, I have normal force acting up. And then I have this other, this is an example of other, because even though I did tell the source of it, the fact that I pushed on my partner is irrelevant. The fact that there's a 100 Newton force acting on him is the important part. It's parallel to the ground. These two forces are gonna cancel each other out. Because as best as we can tell, he's gonna move in a horizontal direction, so he's not going into the earth or coming off the earth, so these two are irrelevant. This is the net force. And so it's just a straight up plug and chug into F equals ma. Now he goes to the moon.
What?
I heard of what?
I use the equation acceleration is equal to,
The F net over mass.
Okay, yep,
same thing as that?
yes.
It's just,
Okay.
The
Sorry,
difference
I
is,
got really confused for a second.
so, when I do plug and chug on this one right here, F equals ma is the way that my brain is fixated on it. So 100 is equal to 70a. That's the math problem right there.
so then you get A.
Okay, okay.
You divide by 70, divide by 70. What you did is you did a as f over m, which would 100 over 70, which is, you get to the exact same place.
Is that, the F is net force, right?
Yes.
Okay, okay.
Yeah, that's one of those things, I think I made a comment in one of the commentaries. But you're just supposed to know that's the total force.
I didn't understand that the force was coming sideways, but now I think I get it now.
Right, Jasmine, and then we'll actually
So
talk about being more
I
specific.
did that and I got the answer of 1.42, what is that, mass? But I multiplied by 9.8, was I not supposed to do that?
No. Alright, so where does the 9.8 come in? 9.8 comes in two different places so far. If something's actually in free fall near the surface of the earth, in other words, something is falling, not being thrown down, while in the act of being thrown, it's, at this point, the only force acting on it is its weight, and it is plummeting towards the ground, or falling, or jumping to the ground, whatever it happens to be. That would then be the acceleration. The other time it shows up is for the formula for weight. So in this particular case, his weight would be 70 kilograms times 9.8 meters per second squared, which is something shy of 700, 600, and 689.
Oh, 686, yeah.
All right, units? I heard it over here, newtons. What is the normal force acting on him?
It'd be 686, too.
Yep. Because in this problem, those are the only two vertical forces and they're canceling out. So,
So it doesn't matter if he goes to the moon,
if he goes to the moon, what changes?
nothing.
Well,
Gravity, weight, gravity.
And
The
again-
gravitational pull.
His weight,
His weight changes.
but his mass does not.
Correct. So the weight changes, the acceleration of gravity is no longer 9.8 on the moon, it's now 1.6 or so. Which makes that 112. And the normal force also changes, because it doesn't have to hold up as much. But on the moon, they still cancel each other out. And so, that stays the same,
So it'd be the same answer.
yes. Because this force is parallel to the ground. If this force were pointing upwards, then, yeah, then that's a different story.
About what parallel?
This is a horizontal force. Other questions?
So for 5 on the master set, with the large truck and the small compact car, I know, or at least I feel very confident that it is the same or equal.
Okay.
Is that correct?
Oh, That you're confident?
That I'm right?
Yes, you're right.
But I don't understand in my head why. Like, I know what the answer should be,
Because Newton didn't lie to us. All right.
but I don't get it.
I want.
I just can't get it through my thick skull.
When you do a demonstration, I do it all the time, you just like do it.
Physical, yeah, I'm much better with physical.
Can you somehow tie this into 6 too, where the small car is pulling the big truck?
Say that again?
Number 6 is where the small truck is pulling the big truck, pushing.
Yeah.
Can you tie this into that, cause I don't understand 6. I
Right.
understand 5, I don't understand. And they're kind of the same thing.
Okay, I think that's enough. Okay. All right, so I got these two scales. And weight to connect them. Oh, we got rings back here. All right, so this demonstration, obviously, it's gonna be very difficult to do with, it's a one-on-one kind of deal. So I'll be glad to do it again elsewhere in the room, or you can take, I guess, Brianna started this, so you can take Brianna's word for it or not. Some people actually need to see it. Let me throw in the caveats, because this is a physics demonstration, don't expect it to work perfectly. Also, one of the things, I don't know, it bugs me that they did this. They have newtons on one side, because it's a scale here. It's known as Hooke's law, that if I apply a certain amount of force, the spring will stretch a certain amount. If I double the force, I'll double how far the spring stretches. So relating the force to the stretch of the spring makes sense. As long as you don't deform the spring, it should work. And then on the other side, they have grams. That makes an assumption of what the acceleration due to gravity is where we are. So it bugs me that they did this, but they didn't consult me. And this is not legal for trade.